Well, it's a lovely afternoon here in Cape Town. It's lunchtime, so I thought I'd just step outside quickly and just make this recording. Last night I did a screencast on Hotteling's t-squared test using R. That is a generalization of the normal t-test. The normal t-test, that's a univariate test. It's a single variable that we're comparing between two samples. With Hotteling's t-squared, we're comparing multiple variables for two samples. Something I think we should do a lot more. Human beings, biological systems are complex systems. We're not just a single variable. We should probably make use of these much more. We should see more of these in the literature. So I'm going to show you one article, but then more specifically how to do it using R. So here we are in RStudio. That is our trusty development environment to write our code in R. So I'm going to do this as an R Markdown file. So if we were just to go to our pubs, where I've already published this, let's go have a look at the document when it's done. Here is my RPubs public page, and you'll find most of the documents that I create for these videos here. The majority of them will be on deep neural networks, but I also do this regular type of statistics, if I can use that term, and I post these documents here as well. If we go look at it, there is the document, the R Markdown document, printed out as a nice HTML page. Now remember, the code will also be available on GitHub, and the links for all of this will be down below. So there is the document that we are going to look at, and we've seen some nice plots there, etc. You'll see some equations there. Of course, you can just ignore those equations. If you want to know more, they are definitely there, but we're not going to concentrate on them too much if you're not interested in them at all. So let's go back to RStudio and let's put this document together. So at the top, there's the usual YAML. So we are going to talk about multivariate analysis of the means for two groups. Now, we know the means of two groups very well with the student's t-test, or the varieties of t-tests. We take a single continuous numerical variable, we take data point values from two samples for that single variable, and we compare the means between those two samples. Here, though, we're talking about something else. We are generalizing that very specific case of a single variable. I can compare the cholesterol in one sample, a sample of patients, to the cholesterol in another sample of patients from the two populations. But I needn't stick to just that very specific case of a single variable cholesterol. A human being is much more complex than that, or for that matter, any organism. A lot of bioscience is all about very complex systems, and you certainly are not just a single variable. You consist of many variables. And it is that measurement, that comparison of all of the means of, say for instance, cholesterol, total some other forms of lipid and blood pressure and serum glucose. So you measure all of those combined against each other. So it's not one-on-one. It's not the cholesterol with the cholesterol for the placebo and the control group, and not just the systolic blood pressure against the systolic blood pressure, but that patient as a whole with all of those variables. We're going to compare two samples across all of those variables. And that is multivariate analysis. So our dependent variables, our outcome has many variables in them, as opposed to just one when we talk about student's t-test. So with a YAML, and back to my R Markdown, just the author there, the output that I like to do is HTML, of course, the table of content to be true, so that when we do see the R Markdown file on RPubs, there's a nice table of content, and I don't like numbering of the sections. This is the normal setup. Remember, this comes standard when you open an R Markdown file. I do set the working directory to the get working directory. So it's going to find where on my file system, on my internal drive, this notebook, this Markdown file is saved, and it's going to set that as the working directory. And I've got everything else, all my other files that I want to use. For instance, we're going to import a CSV file that exists in the same folder, so I can just set the working directory to the single directory. Here are all the libraries that we're going to use: Tibble, Reader, Plotly, DT, MV Norm Test, dplyr, IC, SNP, and Hotteling. And it's the Hotteling's t-squared test that we're after. So if you haven't yet installed those libraries, remember, use the package here, click install, type in the name and install those. I like to just colorize my headings, heading 1, 2, and 3 in my HTML files, that deep navy blue and a bit of a gold color, that's fine. And that is how we import a logo, remember, it's the exclamation mark, and then a set of square brackets, and then just the name of the file without quotation marks, .png, and that asset also lives in the same folder, so I don't have to refer to its whole address on my internal drive because I'm setting the working directory to this current directory that this markdown file lives in. Everything is in that same directory, no problem. So let's just get back to this issue of this more generalized form of a t-test. If we just take one variable, the student's t-test, or the other variations of t-test that we know, it's a single variable measured the means of those at least between two samples. Here we are generalizing the situation and saying, well, we needn't just stick to the specific case of a single variable, we can generalize it to more. So let's just have a look at an example in the literature. So here we are in PubMed. Let's just increase the size here a bit so we can see properly. And I'm searching in PMC, that's PubMed Central, and if you search PMC as opposed to just normal PubMed, you're only going to get articles that are open access, that you don't have to pay a fortune for to view, which in my opinion, as in the opinion of many others, is just the wrong way to go. Anyway, here's a nice little article in the Journal of Oral Maxillofacial Surgery. We see the PMC 2011, October the 1st, published here in the journal itself in 2010, and then comparing actual surgical outcomes and 3D surgical simulations. So of course that was 2010, that software wasn't too advanced. I'm sure we could do a lot better today, but that's not the point of this discussion of ours. What they did, if we just look down at the methods section, you see their Hoteling's t-test. It should actually be Hoteling's t-squared test. But what they did, if we scroll down, they operated on patients, they had imaging, they also did the simulated virtual surgery, looked at the imaging after that, and scroll down, and this is what we look at, this imaging after the surgery, and just different landmarks are colored differently if there was a spatial difference between the two images afterwards. So operating on a patient, operating on the virtual image, and then superimposing those two. That virtual image was from the actual patient, and then seeing if there are differences, spatial differences. How many millimeters were certain landmarks away from each other in the two images? And if it's green, it's very low, into the blue, and then onto the red side, it is more. Now, we can just take certain landmarks, so take the maxilla and the left maxilla and compare just that landmark in that space between these two sets, the virtual image afterwards and the real image, or the real surgery image afterwards, and see what that is. And we can do a t-test there if we meet the assumptions for the use of a t-test, that being a parametric test, and we can just have a look and see those specific differences. So we can go to each of these landmarks. But what we can also just imagine, well, this is a complete and whole patient. The patient does not just consist of that one landmark, and just doing a t-test individually between all of these, that kind of doesn't make sense. And if you think about it, it doesn't really make sense that we just see this abundance just of univariate t-tests. Multivariate is probably what we should see more of, but we don't. And anyway, so you can take all of these landmarks, and so there'll be a column for each and for the two samples, and we can compare the means across all of them at once. That one patient has many measurements, so we are comparing many means against many means all at once. So let's get back to our RStudio there, and if you want to read this, I explain a little bit about that. The assumptions, the Hoteling's t-squared test being a parametric test, we are looking at sort of the a similar set of assumptions for the parametric t-tests. And one is this, the main one probably is this assumption of the sample taken from a population in which that variable is normally distributed, and we can use, for instance, the Shapiro-Wilk test, as we always do, to see that that is true. You also get a multivariate version of the Shapiro-Wilk test, and we're definitely going to use that here just to look at that assumption. Now, it's not as hard an assumption as you might imagine. It is slightly robust against the data not being from a population in which those variables are normally distributed. So it's not the end of the world if it isn't perfectly normally distributed. Now, it just reminds me, we haven't really spoken while I'm doing the screencast about multivariable, the term, versus multivariate. When we use the variate, we're talking about the outcome or the dependent variable side. If that is multivariate, we are measuring more than one outcome, more than one dependent variable. When we talk about multivariable, that means these independent variables that explain something. So if we look at linear regression or logistic regression, we have a model in logistic regression of many variables that can have an impact on a single outcome. So we would have odds ratios and p-values for each of those as they impact this single outcome. Those are multivariables that impact this single outcome. When we talk about multivariate, it is the outcome that we are interested in, and that has more than one variable in it. So don't get confused between multivariable and multivariate. So in that sense, student's t-test is a univariate test. The outcome variable is just the same variable that we measure the means of between two samples. So the second assumption is just that the determinant of variance of the variance covariance matrix must be positive. Now that is a bit of deeper mathematics there. I'm not going to burden you with that. So what we see here is the variance covariance matrix for a multivariate analysis where there are three outcome variables, and I'm going to call them A, B, and C. And as we construct that, what you can see here along the main diagonal, these matrices are always square, and that means that the number of rows and the number of columns are equal, and we can see we have three variables, and then we have therefore 3 rows and 3 columns. Along the main diagonal, square matrix has a main diagonal. That's the one that runs from the left top to the right bottom. That's the variance just of the one variable, the variance of the second variable, and the variance, just the normal variance, remember the square of the standard deviation, along the main axis. And then symmetrically around this we find the covariates. So A and B, A and C, and B and C. And because the covariance between A and B is the same as the covariance between B and A, I've just put A, B in both, but strictly speaking it should be A, B, and B, A. But that doesn't matter because there we go, there's the equation for covariance. In case you've forgotten it, you just take each value, you subtract it from its mean, and the same for the second variable, and so on. And for all of them at least, and you just multiply those, you sum it all up, and you divide it by the total number of subjects minus 1, and that's your covariance. And that's going to go into all of these. And you can well imagine if you're just looking at the variance of 1, that is just the difference squared. So variance, covariance. We should also probably just talk about the dependence between these variables that will impact the results. If some of these variables in your multivariate analysis are dependent on each other, of course, that is going to have some effect on your results. And if they're totally uncorrelated, then that will really add the unique variance to your results, which you actually want to see. Multicollinearity, for that matter, in the independent variables, that will explain variation amongst themselves, but we're really talking about something different here. Just read that, I've put that in the notes. And there's some other assumptions, sphericity, compound symmetry, etc. You can read just a little bit about that. If you want to know more, obviously, you can look it up. So let's just have a look at Hotling's t-squared test. So this is just a reminder of a normal t-test. And by the way, I like to show these. There's my LaTeX there. So that is what you would have to type in to see this nice little mathematical equation on your screen. LaTeX is very easy to learn. You can have a look at that there. So remember t-squared, that the normal student's t statistic, that is just the difference between the two means for the two samples of the same variable divided by this pooled variance, and you see the pooled variance here in the denominator. So the t-squared is different. Here we don't just have a single mean minus the other mean, we have a vector of means. So a vector of means just means there are, in our case, there was A, B, C, that would be 3. It was mean number 1, mean number 2, and mean number 3, and you put them in a little column. That's a column vector, and you make another column vector for the other sample with its 3 means. And that's what we're really interested in. So what we're doing here is we're subtracting these 2 vectors from each other, x sub 1 and x sub 2, and we transpose that. So transpose means if I have a column, a single column of 3, and I transpose that, I will now have a single row with 3 columns. So you just like turn it on its side. That we multiply by the inverse of this pooled covariance matrix, and I show you there, if you're interested, how to calculate the pooled covariance matrix. And we multiply that, these are vector and matrix multiplications, again by the untransposed vector minus the other vector. And if you know something about the dimensionality of vectors and matrices, you know that we're going to end up with a scalar. A scalar means a single value, not a vector of values. And there's our scaling factor there that just has to do with the sample size, and then we get t squared. And we express this t squared in the form of an F distribution, and an F distribution is always going to depend on degrees of freedom. So to get the F distribution, we see there it's d1 divided by d2 times this t squared, or just in another way, if we just look at the number of total number of samples, that is n, and k being the total number of variables, there's another way. It works out exactly the same. So this d1 is just the number of dependent variables, and then d2 is n1 plus n2, that's the 2 sample sizes, minus this d1 variable, the number of variables, minus 1. If you multiply that by t squared, you get f, and then the f follows a certain distribution dependent on these degrees of freedom, and therefore we can work out a p-value, very simple. So let's run a few things. I'm going to go all the way back up because I haven't executed any of these code chunks. So let's go there, going to execute this first code chunk. Let's import all the libraries. You can see the green bar moving down there. That is executed beautifully. Let's move down. Nothing to execute here, nothing to execute here. And here we go. Let's import the data. And I'm going to use read underscore CSV. That is from the reader, R-E-A-D-R library. And that creates a tibble as opposed to a more old-fashioned R data frame. And it's data.csv. It lives in the exact same folder as this R Markdown file. So with my set WD, get WD functions there, I don't have to worry. And then the data table function here comes from the DT library, and that's just going to print a nice HTML, nice little data table to the screen. Let's have a look, and we execute that. It's been imported, and we have this nice data table. You can search, and you can do ascending and descending, show all the entries, move to the second page, etc. It's just a nice way to view a table on a web page. Now let's just have a look at our data here. We seem to have 3. Don't worry about what the values are or what the actual variables are, but every subject has 3 variables, and we want to just compare patients in group 1 and patients in group 2. We want to compare all those 3 combined. So this is a value that lives in this, for this patient, that lives in 3-dimensional space, not on a single line. It's not a single variable. But let's look at them one by one. I'm going to use Plotly for my data visualization. So I'm going to create a plot, and I'm going to call it F1, and that will be the plot underscore leaf function. The data is the data that I'm passing to it. The type is a box, so I want a box plot. Plotly is fantastic because I can use this pipe operator here. So I pipe to that a box plot. On the y-axis, the complaint variable. On the x-axis, the 2 groups. And I give it a name, complaints, and then I pipe that into a layout, and the layout will have a title, and it will have an x-axis with a list which only contains 1 keyword argument, the title. You can view my videos on Plotly. It's, for me, the most fantastic library because it's very interactive. You've got all these buttons there. I can save it as a PNG so that I can use it in a report that I'm writing. You can zoom in, zoom out, do all sorts of things, view it online, to change it online on Plotly's website. But it's very interactive if you hover over that. I really love that. So we can see the sort of normal distribution for the complaints variable. You can see there's a bit of difference between those 2. Let's just have a quick look Let's just have a quick look here at the second variable. We can see its distribution there. Let's have a quick look at the third variable. And there we go. We can have a look at the distribution of it there. So let's just do some of our tests. Now the first one we're going to do is the multivariate version of the Shapiro-Wilk test, and that comes from the MVNorm test library. What it wants though is something very specific. It only wants a data frame or a tibble of the actual numerical variables. So remember we had a fourth variable that contained the categorical variable, the groups. You have to remove that. It only wants, unfortunately, it only wants a sub-data frame or sub-tibble that only contains the variables that we're interested in. So I'm going to create a second variable called data.vars, and I'm going to pipe my data through the select function, and I'm going to use this argument -1_of. So it just means please remove from this data table one of the columns, and it's the group column that I want to remove. So if we were to do that, if we just view these very quickly, there's data vars, and it now only is those three numerical variables, whereas if we looked at data, it has that group with it. So I've just removed that, no problem. Let's just close that up. So now we can use the MVNorm test library, and I put this MVNorm : m Shapiro.test just to show you what library has been used. Of course, you needn't put that, you can just use m Shapiro.test. And another little quirk, it wants that data in transposed form. So if we look at it here, we have the columns at the top, the variables, and then the rows down. It's going to shove that on its side. So we're only going to have 3 rows here, and then all the values are going to be across. So that's transposing it. So you have to transpose it before you pass that. And let's run that test, and we see a W score of 0.9. That gives us a p-value of 0.05. That's very close, but it's still not significant. It's not less than 0.05. So we can say that it passed this test at least, and we can accept this idea of normality. The other assumption that we like to test is just to check that the determinant of the variance-covariance matrix is positive. So COV, it's covariance, that is going to give me the matrix, the variance-covariance matrix, and the det is just the determinant of that, and we want that to be a positive value, and plus 7,853, that's definitely positive. So we've passed those assumptions, and let's just go for the Hotling's t-squared test then, as simple as that. Now I'm going to show you 2 versions of the Hotling's t-squared test, and they come from different libraries. There's the ICSMP library and the Hotling library. So you can use either of those 2 libraries. They both have the Hotling's t-squared test. And they just use different functions for it. In the ICSMP library, it's Hotling T2 and Hotling.test for the Hotling library. So what we want to pass is the 2 sets of data, the 2 matrices of values. So we're going to use dplyr, the filter function. So I'm going to filter the data according to the group column, where the group column equals 1. In other words, that's a Boolean question I'm asking. Take only the ones out that return a true value. So the ones with the group equal 1. And I want all the rows, comma, only columns 1 to 3, because once again, I just want those columns. I just want the numerical columns in there. And then filter data group equals 2. And then again, all the rows, comma, columns 1 to 3. And if we execute that, we see Hotling's 2-sample t-squared test. And there's our difference that we think. We think that the difference between each of the 3 variables should be 0. So we have this vector written here as a column vector, as a row vector, and 0, 0, 0. That's what we expect the difference between that to be. And it's the 3 of them combined, not individual by individual by individual variable. It's the 3 of them combined. And we see the value of df1 there and df2, that's degrees of freedom 1 and 2, and we see a p-value of 0.77. So there's no statistically significant difference between these 2 samples as far as this multivariate analysis is concerned. And then just from the Hotling library, just using Hotling.test, and we're going to see the same value there, 0.771. So we really can't reject the null hypothesis, and we state that there's no multivariate difference between these 2 samples. So in my opinion, a much more exciting way to do your analysis. biological systems, human beings are really not single variable entities or systems. And we should probably make use of this type of analysis much more commonly. Of course, what we do is we do our analysis where we say we correct for all the other variables so that our two samples are very similar as far as all the other variables are concerned, so that we can just drill down on this univariate, especially when we do randomized controlled trials. We just want to drill down on this univariate single variable analysis, and we correct for, or we take out patients so that all the other variables are similar. But it's probably a better way, or we can make an argument for the fact that it's probably a better way just to really concentrate on all of these variables that make up this area of interest that we're studying. And you can well imagine that there are times that we can really make use of this. So what we are doing here is just comparing the means, sets of means, vectors of means of two samples. Of course, you can do that for more. And now we're going to get to multivariate analysis of variance, and you get multivariate analysis of covariance. And even when we talk about regression, you get multivariate forms of regression, where we're going to try and predict a vector of outcome variables. So all of these tests really have multivariate versions, and I really want to make the case for the use of most of them. If I have some time, I might make videos on the multivariate analysis of variance and covariance, and some of the multivariate regression as well. Very easy. All of these things are so easy to implement here in R. So I hope you've learned something. Have a look at Hotling's t-squared test. Look in the literature, find some multivariate analysis. Just make sure that whoever published that didn't make a mistake misusing the term multivariable and multivariate. I've seen that does happen. But just to keep things simple, try and stick to those. Multivariable means those are your input variables or your independent variables in regression models, and multivariate, that's more your outcome or your comparisons as we have here. So try and keep those two terms separate, just to keep things clear.